the series. Glenn Stevens will speak on the p-adic L functions and the eigencurve.
Okay. Thank you. Can everybody hear me?
Yeah.
Okay. So I wanted to talk about the construction of the two-variable p-adic L function. And there are two issues that come in. And so I'm going to deal with them kind of first. The first is the problem of making analytic families of modular forms and things that go with modular forms. And the second is the problem of making p-adic L functions. Okay, so let me start with the easy part. So first of all, the notation n will always be an integer greater than or equal to 1. P will never divide n, will be a prime. Gamma will be gamma 1 of n, and gamma 0 will be gamma 0 of Pn, which is a subgroup of gamma. And I guess I also need an integer. K0 will always be an integer, a non-negative integer. Okay? K later on will be a point in the weight space. So K0 will be a special point. Okay, so the motivating theorem that's been around for a long time, and I apologize for starting with such basic stuff, but I think it's helpful, is due to Hita and Coleman. Namely, if we have a modular form of weight K0 plus 2 for the group gamma 0, it's a Hecke eigenform. And let's say that the eigenvalue of the U operator is some number alpha p, whose p-adic ordinal is strictly less than K0 plus 1.
Why is gamma 0?
Hold on a second. I have my doodad. You could use gamma 1. Oh, I see. Let's let it be gamma 0. Sorry, that's not important. We can fix that. Maybe I should, just to fix ideas, I'll let gamma 0 be gamma 0 of P intersect gamma. That'll take care of all the Nabin types too. Okay? Okay, so then the theorem is that there exists some disk contained in the weight space. Recall that the weight space is the space of continuous homomorphisms from ZP cross to CP cross, and that K0, the integer K0, can be viewed as an element of the weight space. It's what's called an example of an arithmetic point. So the theorem says that there exists a neighborhood, be, say, some aphanoid disk, and some Q expansion, sort of analytic functions on B as coefficients of the Q expansions, where, say, F looks like some sum alpha n Q to the n. The alpha n's are analytic functions on B, such that, 1, if you specialize the alpha n's to any if you specialize the alpha ends to any point in the disk, which happens to be a non-negative integer, then Fk is a classical modular form of weight 2 for gamma 0. And second of all, Fk0 is the form we started with. Okay, so basically what this theorem says that if you take almost any classical eigenform, there's some p-adic analytic family that passes through it. The only thing that's not been discussed is the case of critical slope because of the condition on the p-adic ordinal. The p-adic ordinal can be at most k0 plus 1. And so there's only, that's called the critical slope case, and that's been pretty close to handled now as well. Okay. So let me just give, just to be very concrete, 2 examples, just to see it. The first one is the family of Eisenstein series. Which looks something like this. The sigma k plus 1 star of n is the sum over the divisors of n that are not divisible by p of d to the k plus 1. And so the point is that if k is any point in the weight space, my notation, by the way, if I have a unit zp cross, my notation for the character evaluated at u is u to the k, so that it matches with the integral powers. And so since the d's here are always relatively prime to p, each term in this sum is an analytic function of k on the weight space. And so this q expansion is zeta p of minus 1 minus k. That's the Kubota-Leopold p-adic zeta function. And so we see this beautiful family of q expansions. And in fact, if you specialize that family to any weight k integral greater than or equal to 0, where the weight would be k plus 2, but you'll get a classical Eisenstein series. So that's a very typical example. It's the only, well, almost the only other example where one could give explicit formulas would be for families of CM forms. But here's another example. Think about the case f is q times the product 1 minus q to the n squared times 1 minus q to the 11n squared, where n is greater than or equal to 1. That is a cusp form for gamma 0 of 11 of weight 2. And think about the Ramanujan delta, that's q times the product, n greater than or equal to 1, 1 minus q to the n to the 24. So that we know is a weight 12 cusp form for gamma of 1. And then I invite you to notice that these two q expansions are congruent modulo 11. Okay, just a simple glance at that will verify that. Now, in fact, the delta doesn't live on gamma 0 of 11. You have to modify it. Delta has 2, if you look at the characteristic polynomial of Frobenius at 11 for delta, it has 2 roots, alpha and beta. One of them is a unit mod 11 and the other is not. And so let alpha be the unit root. And then define delta alpha to be delta of z minus beta delta of pz. And I invite you to see that delta alpha is also congruent to delta mod p. P is 11 now. And so here we have an example of 2 forms whose q expansions are vividly congruent. And the theorem, in fact, is that there's a beautiful p-adic analytic family, 711 adic family, that flows from that form at weight 11, at level 11, to that form at weight 12. And not only that, but if you specialize it to any integral point in between, and by in between, I don't mean in between, I mean any, there's a lot of them, there are infinitely many of them. Every single one of them will be a classical form of some of the corresponding weight. Okay, so it's like this amazing thing that you can piece these Fourier expansions together in such beautiful analytic fashion. Okay, so that picture is really, really important. And now I'm going to go and say, hold on, I can do this. I'll learn how to write on the paper. Hold on. Should I be writing this way, maybe? Okay, so the eigencurve. The eigencurve is a beautiful way of putting all of this together. In the picture I just described with these two forms, the parameter of the analytic variation is the weight variable. But in general, that's not the way it works. In general, you need to be a little fancier. You need the eigencurve. Okay, let me just describe it. So this is a theorem due to Coleman, Mazur, and Buzzard. There exists some stuff. Okay, and I'll write it down. There exists, first of all, a curve, C. It's a rigid analytic curve. It's p-adic. The curve also comes, the part of the data is a function that goes to the weight space. So W is the weight space that we described already. And K is some locally finite map. Rigid analytic map. And so just so that I'm not confusing anybody, this rigid analytic curve, this is not a finite cover. It's not a finite map, it's only locally finite. So let me try to draw a picture. Here's the weight space. And then the curve C maps down to it by something. So you have something like this. It might have some components. But the key here is that it goes up and up and up and up like some giant squid going off to infinity. And then there's a weight map that pushes down. Right? That's K. So this is C and this is W and etc. So some picture like that. Okay, so what properties does it have? Such that. So first of all, there's a one-to-one correspondence between, so let me say first of all, so having fixed K, so with fixed K0, say, in the weight space. Now this K0 doesn't have to be integral, sorry. Such that for any, there's a one-to-one correspondence between the following two sets. The set of all points, x in C of k, k over qp, some finite extension, x in C of k, such that the weight of x, the projection down, is k0, is in one-to-one correspondence with the set of overconvergent eigenforms f sub x in m modular forms of weight k0 plus 2 that are overconvergent for gamma 0 with coefficients in k, such that alpha p of that form is not 0. Okay, so in other words, over here, if I pick a point k0 on the weight space and look at its fiber, these points in the fiber correspond to overconvergent p-adic modular forms that are eigenforms and have that weight. And the extra condition, by the way, that alpha p is not 0, that's called the finite slope condition. Okay? Finite slope means that the p-adic valuation of alpha p is not infinite. Okay. Okay. And B, there exist rigid analytic functions alpha n on C, such that for all x in C of k, if you take the form associated to that point, the overconvergent form, its Q expansion is alpha is the sum alpha n of x q to the n. Okay, so the x, you see, is the parameter. And then there's an extra little piece, which I'll just add for amusement. Moreover, C is smooth and unramified over the weight space at every classical point. Of non-critical slope. So with the exception of the edge. And I think Belaish has even proved that it's smooth there, but that's a fairly recent theorem. So let me cross off with a non-critical slope and say by Belaish. It's a little bit different there. It's ramified, that's what's missing, right? That's what's missing. So I have to, what I said is correct. The way I wrote it the first time, Belaish, if you get rid of the unramified statement. Okay, still smooth, but it's not unramified. It's unramified at the points of non-critical slope. Now, the point of being unramified at points of non-critical slope means that if you're sort of, if your non-critical slope is like small slope. And so for small slope, being unramified and smooth at that point means that you can think of a neighborhood in the Eigen's curve as being isomorphic to a neighborhood of K0 on the weight space. And so what Hida and Coleman were seeing was that variation down here in this particular case. So thinking up here, thinking down there in that case is no different, but you run into trouble when you run into the ramified points or non-smooth points. I haven't drawn any bad points, but there can be bad points too. What it does, they can cross and things like that. Okay. Okay. Okay, now, I actually prefer my picture. Now, the problem in general is what this curve does is it pictures the variation of a modular form. Now, we all know that modular forms come with lots of extra data, like Galois representations. They come with cohomology classes. They come with p-adic L functions and things like that. And so the idea is that as you move the modular form, you want to keep track of how all of that other data moves along with it. Okay? And so that's basically the strategy for making two variable p-adic L functions. It's really that simple. We make one variable p-adic L functions at each point and then move them. Okay? Okay, now I'm going to run out of time, of course. So, so first of all, let me just say that the classical approach, let me just state the theorem of Amis and Velou. If we have some slope, some form whose slope is less than k0 plus 1, then there exists a unique p-adic L function satisfying certain conditions. And I'm going to suppress the exact statements. But the first one is interpolation. In other words, the p-adic L function should be, you should know what it is at certain points. I'll draw the points. And the second one is that satisfying LP of F is tempered of order slope of F. Okay, the condition of being tempered, let me just draw the picture. The p-adic L function is a function on the weight space, taking values in CP. And the weight space is a bunch of disks, open disks. And on each one, you've got the integral points. You've got 0, 1, 2, 3, up to k. And you can take any of those and multiply by finite order characters. That gives you a lot of characters, a lot of points. So the interpolation is at those points, and you get a bunch of such points in each of those disks. So the interpolation is there. The statement of being tempered means that if you restrict the p-adic L function to some disk, now it's bounded. But as you move towards the boundary, the growth, the supremum of the p-adic L function on those disks, as the disk gets bigger and bigger and bigger, it grows. And that's called the growth rate of the p-adic L function. And that can all be written down very carefully. And so tempered of some order is a statement about that growth condition. So there are interesting things to notice, and that is that the interpolation property, so long as the slope of the modular form is non-critical, the interpolation properties are enough to uniquely determine the p-adic L function if it exists with these two conditions. But if the slope is critical, it's not anymore. Critical slope allows the function to grow faster. It's allowed to have more zeros. And so if you had two functions that interpolated the same difference, the same values, their difference would be a function that is 0 on a bunch of points. And the being tempered of a certain order says that you can't have too many zeros on average in small disks as they grow. And so when the slope is critical, that condition isn't strong enough to guarantee that that difference is 0. That happens at the critical slope. And now, in fact, we're trying to make p-adic L functions not just for those classical points, but we're also going to make them all along the eigencurve. And so there you don't even have nice interpolation formulas to play with. And so the interpolation strategy in the end doesn't work. And so what we do is we use modular symbols. So modular symbols. And I'm assuming that this has already been talked about in some detail. Okay. So since I'm going to run out of time, let me just say a few extra words that might not have been said. One is, did you talk about the compactly supported cohomology? Compactly supported cohomology. Okay, let me just make that remark. So we've thought about modular symbols for, say, gamma 0 with the values in module M. And this is, by definition, Hom gamma 0 divisors of degree 0 on P1 of Q, taking values in M. It's a very simple thing. It's something that you can compute. The beauty of this is that just about everything that I'm going to say seems to be computable on a computer, which I still find amazing. Okay, now, so theorem. This is due to Avner, Ash, and myself some time ago. If the number of torsion elements in gamma, or the order of each torsion element, acts invertibly, on M, then there's a canonical isomorphism between that and this modular symbol thing. When I say gamma, I'll say gamma 0. Okay, works for any congruent subgroup. And so the way we think about this is that if you have a modular symbol, say phi is in here, then I like to think of it as a cohomology class. And I like to think of it as something that one can integrate from one cusp to the next. And so sometimes we'll write phi r to s. That's just another notation for phi of the divisor s minus r, I guess. Or, yeah. Element of M. The advantage of this is that you can play games with compactly supported cohomology. It's functorial. If you have a homomorphism from M to some other module, M prime, then that induces a map. You see that in the level of modular symbols too, but it has all these nice properties of a delta functor, and that's nice to use sometimes. Okay. Okay, now, the reason that by the way, this notion of modular symbol, not quite in this generality, but the first people to talk about modular symbols were Barry Mazer and Swinnerton Dyer back around 1974, 75, and they were studying values of L functions. And so the idea is that values of L functions, they encode arithmetic data about global arithmetic gadgets that you might be looking at, like a modular form. But at the same time, the L values themselves are arithmetic things. And so you can do arithmetic with the L values themselves and learn something about the arithmetic of the global object that's being reflected by these things. And so I like to think, when I think of a modular symbol, I think of it as a kind of L function. Okay, and to be very precise, we define lambda of phi to be the Mellon transform of phi. That's phi, you go from infinity to 0. Let's call that the universal L value. And so you make L values by making cohomology classes and then integrating from infinity to 0. Okay? Okay, I'm going to skip the main example because I'm assuming that Rob has already shown you exactly how to connect what I just said with special values of L functions of cusp forms. Okay, if you take up a cusp form, let me write it down very quickly. If F is a cusp form, then let omega f be 2 pi I f of z, zx plus y to the k0 dz, where this is a one form on the upper half plane, tensor sim k0 of c. So it's like a one form taking values in this vector space. I like to call this, I will call this sometimes L K0. It's a finite dimensional vector space. Gamma 0 acts on it in a natural way. And integration. So I define psi f from R to S to be the integral of omega f. That's in LK. And so in particular, lambda of psi f is an element of LK, the universal L value of psi f. If you write it out, what you see, you get that lambda of psi f is a polynomial, and its coefficients are honest special values of L functions of f. And so the difference between universal and special in this case, the universal L value is lambda of f, but if I can compose, say, the module with some linear functionals like the coefficients or something like that, I get special values of the universal L value, that kind of thing. Okay? Okay. Amazing. Okay. So our strategy then is to make some very interesting cohomology classes. You see that when we make the modular symbols, this module M can be virtually anything you like. And so the idea is to make the module M very big so that the universal L value, it lives in some very big module, and so it has lots and lots of special values. Okay? So, man, that's sort of the feeling of it. And so the big module is going to be some space of locally analytic, p-adic locally analytic distributions on something, say ZP. Okay? So let me just talk about locally analytic distributions. This will be our module. So let me think about ZP and think about this is the space of locally analytic functions on ZP. Okay, so by a locally analytic function, I mean a function on ZP, it'll be continuous. And on any disk, or at any point, I should say, there's a disk on which the function is given by a power series. And so you might think of the function, for example, might converge on the entire closed unit disk. That would be great if the whole thing would be given by one power series. Or it might underconverge on just some union of a finite number of closed disks inside of ZP, one for each congruence class, say, modulo p to the n. That would still be an example of a locally analytic function. Okay, and so in the end, A of ZP becomes, I should say that the functions on the closed unit disk, that's a Banach space, that's the Tate algebra. Whereas if you sort of specify a level of underconvergence down to just disks of radius 1 over p to the n, say, then you also get a Banach space, but it's a different structure. And so the A of ZP can be thought of as an inductive limit of Banach spaces. And there's a natural inductive limit topology that goes on such a space. In fact, this particular limit is an example of a compact inductive limit, meaning that each inclusion is a completely continuous function. Okay. So anyway, so there's that. It's a topological space. That's my point. And so I can think about D of ZP. D of ZP is the space of continuous linear functionals on A of ZP. Okay, now A of ZP was an inductive limit, and so the D of ZP is naturally a projective limit. Okay, also with compact connecting maps though. Okay, now, so let me just try to make this clear. So now to make p-adic L functions, the idea is to make an element of D of ZP. And so we take D of ZP, and we take a mu in there. So we're going to make elements of that by using modular symbols. But once we have one, then what we'll do is we can restrict our distributions to functions that are zero outside of ZP cross. So there's a restriction map. And then I'll define the p-adic L function of mu at S to be, I'll take the integral over ZP cross of T to the S minus 1 d mu of T. Okay, the notation is just funny notation. All this integral means is, think about the function T goes to T to the S minus 1. That's a function on ZP that is zero outside of ZP cross, and on ZP cross is T to the S minus 1. It's an example of a locally analytic function. And so mu can be evaluated on it, and that will give me an element of CP. And it turns out, when you look at that carefully, that the function of S that you get is a nice rigid analytic function. This is rigid analytic in S. And of course, S can be anything in the weight space, any continuous homomorphism of ZP cross. Okay, so let me just remind you of a theorem, which maybe Rob's already said, and that is that if I take D of ZP cross, there's a natural map from there to rigid analytic functions on A of W given by what I just wrote down. And this is an isomorphism. And so the space of distributions on ZP cross is nothing more nor less, or is isomorphic in some canonical way, to functions on the weight space. And so the p-adic L functions I get this way will be functions on the weight space, and I get all functions on the weight space that way. Okay. Okay, and so now gamma 0 acts on A of ZP in many ways. One for each weight, depending on the weight. Okay, and so the action that I'm going to have in mind, I'll just write it down quickly, though I suspect you've already seen it, is I think of gamma of a function, this is not a form of Z, to be A plus CZ to the K times F of Z gamma, where Z gamma is some fractional linear thing. The thing to notice is that since C is divisible by P, and since that determinant is a unit mod P, the A plus CZ is in ZP cross. And so it makes sense to take that to the kth power for any point in the weight space. Okay, and that defines a nice action. We get an action of gamma 0 then on A of ZP, and that induces an action on D of ZP by duality. And that's our action. And so our goal then is to make some interesting modular symbols over gamma 0, taking values in d of zp. Okay. And so that's what we're doing basically. We're going to study H1 compact support gamma 0. By the way, this action that I've described here depends on the weight. And so when I do this, I should put a K down there under the A to remind me that I'm talking about the K action. And when I put the dual action here. Okay, so we're going to make some interesting cohomology classes. So the first thing is to notice that the first thing to notice is that the space of polynomials of degree at most k0 is naturally contained. These are examples of locally analytic functions. And in fact, that's a closed subspace. And so by duality, we'll get a map from dk0 back to pk0 dual, which just happens to be the space lk0 that I wrote down before. And so we have a map from this space. So if k0 is non-negative, we have a map from dk0 to H1 compact support gamma 0 lk0. And this is the specialization map. And I know Rob talked about this yesterday. And so the theorem is that when the slope is small, if you have a form, you can make sense of this statement. If 0 is less than or equal to h is less than k0 plus 1, then the slope less than, well, I can even do this less to h is isomorphic to this thing. I'm sorry. Okay. And so, so the point here is now, I'm sorry. The better. Okay. All right. And so by the comparison theorem, if I start with some classical eigenform of slope less than k0 plus 1, I better say S, and I think about its modular symbol, that will be, there are actually two of them. I'll get something in, let me say first of all, lk0 slope less than k0 plus 1, but this is isomorphic to H1 compact support with coefficients in dk0 slope less than k0 plus 1. And let me call that lifting phi sub f plus the same thing. And so that phi sub f then is naturally attached to the cusp form. And so in particular, you can think of its Mellon transform. Its universal L value. And then define that to be mu f, and then LP f s is by definition LP mu fs. And this has all the properties. It is, in fact, in the case where the where the slope is non-critical. This is the Amis-Filou p-adic L function. But the point here is that this idea has the possibility of generalizing to other non-integral weights. Okay. Okay, and so let me just make a definition of the cohomological eigencurve. So if line C to be the set of all homomorphisms from H to, say, CP. Let me define C of K, where K is my field, just to be sure. Where this H here is now the Hecke algebra. Such that C occurs, in some sense, in the cohomology of D K for some K. And C has finite slope, meaning that the eigenvalue of the U operator is not zero. Okay? So this is something that can be made very, very precise, in fact. And it's a theorem that is isomorphic to the Coleman-Maser eigencurve. In fact, the Coleman-Maser eigencurve, remember, the points classified Fourier expansions of eigenforms, but Fourier expansions of eigenforms classify homomorphisms on the Hecke algebra. And so this is the same set of objects. Not only are they isomorphic, they're equal. That's the right way to say it. Okay, so let me just very quickly sketch how you do this. So we have to spread things out. So think about A as being locally analytic functions on ZP cross ZP. So before it was just locally analytic functions on ZP, but now I'm allowing two variables. We have a natural action of gamma 0 on that as well, by just a linear change in the variables. And we let D be equal to, again, this is has a natural topological structure. Structure is a p-adic topological vector space. And let D be the space of continuous linear functionals on that. Well, in this case, you see we have D is a module for gamma 0 by duality, but the action of ZP cross on this product, ZP cross acts on vectors of that type, induces an action by convolution I should have said that D of ZP cross, since ZP cross is a group, that's an algebra, it's a convolution algebra, and you get a beautiful action on it. This is, remember, by Amis, is just isomorphic to the space of rigid analytic functions on the weight space. And so this D, the spread out version of D, is on one hand a module for gamma 0, and on the other hand, it's a module over the ring of all rigid analytic functions on the weight space. Okay? Okay. And then you define, the idea then is to try to make a phi living in this, okay, which is an eigensymbol. I'm going to run out of time, so I'm going to tell you what you try to do, and then admit that you can't do it, but you can almost do it. Okay. You try to make an eigensymbol. If you were able to make a good eigensymbol that's specialized in good ways, then you would again take its special value. You would let mu be lambda of phi. That would be a distribution on ZP cross ZP. And then you would define the Pollack function to be the integral over ZP cross ZP cross of x to the k y over x to the s minus 1 d mu of x, y. Okay? So that's what it would look like. Yeah, if you do that, by the way, if the phi has any good properties, like it's an eigensymbol, and so you're going to try to extend it to a distribution on ZP cross ZP. In fact, you can do that in an interesting way to move into a space where gamma itself acts. And if you do that, you have a W involution of level n, and you can use it to define things like functional equations to prove that the interchange of the variables y and x can be done in some reasonable way. When you do that, you get a functional equation that the Pollack function satisfies. When you specialize to integral weights, it'll specialize to classical forms. The only problem is that I'm not able to make such a phi except in special cases, like the ordinary case, for example. In Hita's case, one can do it. Okay. Okay, so now let me just very quickly, I'm going to stop in like 2 minutes, but the idea is we're going to start with cohomology classes in some LK0, modular symbols taking values there. And then we have distributions of weight K0, and that maps by the specialization map that I described and Robert has talked about. And then back here, we have D, the thing I described over here. Now, what you have to do is you have to put something in between. You can't deform all the way out to make a family that lives over the entire weight space for exactly the same reasons that when you look at families of modular forms, you can't do it. In that case, you have to generalize along the eigencurve. But if you, so long as you stick to some sufficiently small neighborhood of the point K0, that omega contained in the weight space, an aphanoid neighborhood, of K0, and then d omega is by definition d tensor over d of ZP cross with the ring of aphanoid functions on omega. It turns out that you can, in fact, you need for this some sort of, I'll just say using Coleman's. Robert Coleman did all of this in his original papers. He did all the foundational stuff using Robert Coleman's theory of orthonormalizable Banach modules. And the theory of Fredholm and Ries. Applying it to this space, basically, you can get a decomposition. I don't have time to describe it, but it involves taking what's called the characteristic Fredholm series of the U operator, the characteristic Fredholm series of the U operator acting on D. I'll just write it down and stop. Not on D, but on this, whatever that means. you get some, what you really do is you do it for each omega, and you take some limit. You get some power series, which lives in lambda t, where lambda is the Iwasawa algebra. And then what you do, so there's a power series whose coefficients are the elements of Iwasawa. And the Iwasawa algebra is a ring of functions on the weight space. Now you restrict those functions to the omega that you have in mind, and you get something p omega, just restriction. That lives in A of omega bracket t. And what Coleman did is he showed that by taking omega small enough, you can make that p omega have a nice finite factorization. You can factor off a polynomial. This thing is a power series. You can get a factorization, and you use that factorization to chop up the cohomology into a finite rank piece, and then some infinite dimensional piece that's too big to keep track of. And so all of the lift things live in that finite dimensional case, in that finite dimensional part. Okay, so we can talk about this later on, but I think I should stop for now. Okay.